So another fairly easy one. So we've got a aircraft, it's on the tarmac. So it's sitting on the ground, they're testing the engine, so they're driving one forward, they've got a force of 2 kilonewtons forward, and then the other engine they're driving backwards, so it's 2 kilonewtons backwards. These are the wheels here, they've got those brakes so that the plane doesn't actually turn. They're just running a test. And so it wants to know the moment about the nose of the plane due to the engines running in opposite directions. So they're asking for the moment about the nose, but because this is a couple, as we've already discussed, it doesn't really matter which point you choose. You could choose the tip of the wing, you could choose the center of the aircraft. It's a couple. The moment is going to be the same at any of those points. So the moment due to a couple doesn't change with the point that you're measuring it relative to. Okay, so again, simple formula is moment is equal to force times lever arm. So the magnitude of one of the forces times the perpendicular distance between the lines of action of the parallel forces. So in this case, that's equal to now direction. This time we're going, just mark it on, these are going to rotate the aircraft anti-clockwise, so it's positive. So force times distance. So it's going to be 2 kilonewtons, you're just taking one of the forces, not both of them, you don't add them together or anything, times 5 meters, so it's 10. We're using kilonewtons this time, it's a moment, so it's 10 kilonewton meters. That looks okay. So they've asked for the moment about the nose, so we'll just give them the answer they want. Moment about nose of aircraft is 10 kilonewton meters. And we could put in brackets anti-clockwise, but using the arrow is quite a nice way to do it. So we'll just call it anti-clockwise. And so let's just draw the arrow to show the direction, 10 kilonewton meters that way. Just bear in mind, if you're using that arrow to show the direction of rotation, best not to write something like 2, if you're talking about a force that's clockwise, and say it was 2 kilonewton meters clockwise, don't then do negative 2 kilonewton meters and draw a clockwise arrow. Use one or the other. So if you wanted to show that, that would be equivalent to, so for equivalent to, it's like an equal sign with an extra line. That would be equivalent to 2 kilonewton meters clockwise. If it try and draw, it's half decent. So 2 kilonewton meters clockwise. Okay. So the next part of the question, so that was part A. Part B, they're saying what's the force on the wheel? So it's just asking for a force, not asking about directions of that or anything, but nonetheless, let's have a think about it. And so the wheels are kind of back here somewhere, so they're 3 meters apart. I think in this one I've used the scale of 1 square is equal to 1 meter. So the wheels are there somewhere. Let's just draw the lever arm. There's the perpendicular distance between the forces. It's going to be 3 meters. And the moment must have the opposite orientation because the sum of the moments, so you're kind of talking about static equilibrium. You're figuring out how the plane is going to stay in the same place. Static equilibrium, your forces must add up to 0. Therefore, the force from this couple must be in the opposite direction, must be clockwise. So we'll need the force to be going this way. What do we call this force? We'll call it FB maybe, or FW for the wheel. So this is FW, FW. So moment, I don't know why I'm doing blue. So moment is equal to FW times the lever arm between the wheels. Not worrying too much about positive, negative. Really, it's negative 10 kilonewton meters. But they just asked us for the force of the wheel, so it's kind of asking for a magnitude rather than a vector here. So FW times DW must be equal to 10 kilonewton meters. Therefore, FW times 3 is equal to 10. Therefore, FW, divide both sides by 3 and you get 3.33 kilonewtons. It's a force, so that's in kilonewtons. So force at braked wheel is 3.33 kilonewtons. We'll underline both those answers just so they're easy to find. Okay, another one bites the dust. So we'll move on and just look at another little theory or concept now of finding a resultant vector of a heap of different, or a resultant force and moment for if you're applying lots of different forces and couples to an object. We'll have a quick look at that, and then we'll be done for this week, and we'll just look at how we apply that to a whole slew of examples. Okay.